So hello everyone. So today let's solve the problem number 133, clone graph, right? So let's see what the question states here. We are given a reference to the node in the connected undirected graph. Yeah, let's come to the first example here. They have given the figure. Let's see what the figures basically trying to say here, what they are trying to say here, right? So just give me a second here. Yep. We are given a reference to the node in the connected undirected graph. This is fine. So all we need to do is we have to return a deep copy, nothing but the clone of the whole graph, clone of the whole graph, right? Right. So they have given the reference to the node in a connected undirected graph. All we have to do is we have to return the deep copy, nothing but the clone of the whole graph. Each node has a unique int, this one basically value, and a list of neighbor, nothing but the nodes actually. So input uses one indexed values, right? So just remember this one, this is very important. Input uses one indexed values, right? So we have to return the cloned reference corresponding to the input node, right? So node with value that is equivalent to the one, we have to use it, we have to go with a node with value that is equivalent to the one for the non-empty graphs actually. Yeah, so this one I can just show it in this way, node with a value 1. So this is fine. So let's consider this one. Basically we have 1, 2, 4 and 3, right? So this is the original graph. We cannot return the same graph. So we can just go with return this one, right? So whatever the parameters that we have given, we just return, we'll get the answer. No, we have to go with a deep copy. We cannot return the same graph. They have strictly mentioned here, right? So this looks like a clone actually. This looks like a clone, but see here, this actually looks like a clone, but here in this case, uh, this one, these nodes are the nodes are new, graph looks the same actually, graph looks the same, right? So this is the correct one actually, sorry, this one is the correct one actually, right? So this looks like a clone they have given here. See, uh, we can't return the same graph, so that is one thing. So the nodes are new and we have to go with the new nodes, right? So the nodes are new, graph looks the same. So this is actually the clone, so this is fine. Then comes the third one. See here, they have given uh, this also looks like a clone, but see here, the values are different. The values of the nodes are different. So we have one instead of the two, we have three here. Instead of the two, we have three here. So that this is wrong, right? So instead of the so this one instead of three here, see we have three, but we have two here. So this is wrong, basically. Yeah, this cannot be a clone. See here, the nodes were cloned, but the graph is messed up here, doesn't have the same connection. So this is also not possible. This is also not possible. The correct one is this one, the second one. Yep. So they have given us wonderful diagram here just for the sake of understanding, right? So the output that we need to get here is same one. Yeah. All we have to do is we shouldn't return. Instead, we have to go with the deep copy. Yeah. So this is fine. So the same thing, example here, we have the empty. So we can just output this one, the output that we need to get here as empty as well. Yeah, same goes with the third one as well. So this is an empty graph. It does not have any nodes. So this one. So here the input contains one empty list. So this differs from the complete empty graph. This consists of the empty list. So the graph consists of the only one node with a value equals 1 and it does not have any neighbors, right? So these two are different, a bit different, right? So this is complete empty graph and this is with the value equals 1. Nothing but we have the one empty list actually. Yep. So this is fine, man. They have given us wonderful examples just for the sake of understanding. So let's do one thing. Let's discuss the approach. Yeah, let's discuss the approach. Then we can just discuss the complexities and then let's write the code, right? So let's come to the approach part. So I'll just do one thing. Let's consider the first example for the approach. Let's consider the same example, this one actually for the approach. So 1 second, man. Yep. So first thing here, we'll start at node 1 actually. So this is the graph actually. Given 1, 2, same thing actually. 4 and 3. Yeah. So this is the graph that they have given. Yeah, we'll start from the node 1 initially. So we'll create clone 1 and we'll put the mapping original here. So clone in a map basically, right? So we'll start from the node 1. So the second step here would be using the BFS. So one thing I wanted to tell you before itself. So we will be making use of the BFS to solve this particular problem. Yeah. Breadth first. Such. So we will be making use of the BFS, nothing but BFS uses queue. We know this, right? So we'll be making use of the BFS. First, what we'll do, we'll pop the original node 1. So we will be popping this original node 1. So this is fine. So next, what we will do, we will iterate the neighbors 2, 4. We'll iterate the neighbors 2 and 4. We will be iterating the neighbors 2 and 4 respectively. For each neighbor, if not cloned yet, we will create its clone. Yeah. For each neighbor, if not cloned yet, we will create its clone and will enqueue the original neighbor, and we will enqueue the original neighbor. Then we will add the clone, nothing but neighbor to the clone 1, neighbor to the clone 1. So these are the neighbors to the this one, node 1, right? One is 2 and another one is 4. So that's what we'll be doing actually. Next, what we will do, we will continue with original node. So this one will continue with original node 2 actually, this one. Yeah. So neighbors are this one, basically 1 as well as the 3, these two. 1 is neighbor to the 2 as well as 3 is neighbor to the 2, right? So 1 and 3 are the neighbors here. What we'll do, we'll clone 1 already exists, so this one already exists, we don't have to worry about it, right? So we'll create clone 3. So this is the neighbor of 2, so we will be creating the this one clone 3, and we will enqueue 3, right? So we'll enqueue 3, we'll link clone 2 and clone 1, and then we will clone 3 actually. So we will link clone 2 to the clone 1, and then we will finally clone 3. Yep, so this is fine, I believe. So the next step would be here, we will be visiting the original 4. We'll be visiting this one 4. We have visited 1 and 2 respectively. Uh, so let me draw this one again. So now 4 as well as the 3. So we have already visited 1 and 2, right? So this is fine. Yep, we will visit the original 4 now. Neighbors to the 4 are 3 as well as the 1. This one, 3 as well as the 1 to the 4, right? Neighbors are 3, this one. What do we call? 1 and 3 basically. So clones already exist. So for this one, 1 and 3 clones already exist. By looking at this itself, we can say clones already exist for 1 as well as the 3. So this is fine. Yep. So we will link the clone 4 appropriately. We'll just link the clone 4 appropriately. So this is also done. Now we will visit the original 3, right? So we are left with only 3 actually. So let me show you this one as well by drawing another graph. So we'll visit the original 3. So we have the neighbors for 3 neighbors are this one 2 as well as the 4 respectively. Now both clones exist, so we will just link. So both the clones exist, 4 as well as the 2. One also actually exists. We have already cloned this one. So both the clones exist, so we'll just link. So after BFS finishes every original node, so after BFS finishes, every original node has a unique clone with the same neighbor structure, right? So we'll just return clone 1. We'll just return what we will return. We'll just return clone 1 here, right? So this is the advantage of making this one. This is the advantage of using the BFS, right? So this is it, right? So this is it for the approach. So the output that we'll get, the same output that we'll get, right? So this is fine. So now as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to big of n plus e, right? So the time complexity would lead to big of n plus e. When I say the time complexity would lead to big of n plus e, we visit each node once and we iterate each edge exactly once. Nothing but the we'll be performing BFS here, right? So this is fine, man. So what will be the space complexity here? The space complexity would lead to big of n here. So basically why it is big of n here? For the map of n clone nodes plus BFS cube, both are of big of n, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n plus e and big of n respectively. Yeah. So now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. They have just shown the definition of node here. Let me clean this up, man. Yeah. So this is fine. It doesn't matter. Anyways. Uh yeah, that was just for the reference, man. Yep. So now let's start writing the code. First thing here would be if the input node is null. If the input node itself is null, there is nothing to clone. In that case, we have to return null, right? So I can just write it in this way. If node equals null, let me return null. Yeah, this is fine, man. The next step would be we have to map to hold mapping from the original node to its clone node, right? So I'll just go with here map of node comma node. Yep, comma node. So let me go with node here. This is fine. I'll just go with map equals new. Let me go with hash map here. This is fine. Let me complete the syntax here. This is fine, man. Now let's do one thing. The next step would be let's go with a queue for the BFS traversal over original graph, right? So I'll just make use of the BFS, quite obviously uses the queue, right? So let me give here node queue equals new array dq basically. This is fine. Yeah, array dq. Yep. The next step would be we have to create the clone of the start node and we have to put this one, put in map actually. Yeah. Let's move on with the further things. Basically, let's do that. So this will be node clone actually. So this one will be new node of node dot value. So this is fine. We are just cloning for the node. Next, I'll just go with map dot put actually. I'll just go with the node comma node clone. Yep. So this is fine, man. Now, what shall we do? Let's start the BFS by enqueuing the original start node. So this one will be q dot add of. Let me pass the node over here. So this is fine, man. So the next step, let's go with a standardized BFS loop. Nothing but we have to visit every original node and build the neighbor links and the clones, right? So I'll just go with while here out of q dot is empty. So this is fine. So within the while loop, let's go with the original current node here. So this one will be node current equals q dot poll. Yep. So this is the first step usually we'll be going with when we are making use of the standardized BFS loop within the BFS. Next, for each neighbor of the, we have to consider for each neighbor of the original node, right? So let's move on with the iteration part. So this one will be for node. Just consider for the neighbor, individual neighbor. So this one will be current dot neighbors, right? So this is fine, man. So within the for loop, if the neighbor hasn't been cloned yet, then we have to create the clone and enqueue the original neighbor, right? So I'll just go with a simple if condition here. If not of map dot contains key, so this is fine. Let me pass the neighbor nei. Then within the if condition, let me do one thing. Let's create the clone for the neighbor. So this one will be node a clone. So this is fine. It will be new node of I'll just go with the neighbor dot clone. Sorry, not clone actually, value, right? So val is the keyword that we have to consider. This is fine. Now we have to store the mapping as well. So let me go with a put actually that the hash map provides here. So let me pass nei along with the nei of. So here we have to pass clone actually. Yep. So this is fine, man. Why I have considered this one parenthesis here, not nei of clone. So this one is nei clone, neighbor clone actually. So this is fine. We are just going with the this one. We are just storing the mapping here. Next, what we need to do, we have to enqueue the original neighbor to explore its neighbors later. So this one will be q dot add of neighbor nei. So this is fine. Let me come out of this one entirely. Now let's link the clone of the current node to the this one clone of this particular neighbor. So this one will be map dot get of, let me go with the current. So this one neighbors. So this is fine. Dot add of this one. What do we call map dot get of? So I'll just go with the nei, right? So this is fine, man. So I'll just come out of this one entirely. We are left with only one thing. All we have to do is we have to return the clone that is corresponding to the input node, right? So I'll just keep return here. I'll just go with a node clone. Yeah. So this is it for the code. Let me format the code once and let me hit the run button. Hope this works for all the test cases. Let's see. So this has to be node. I have given node here. This is fine. Yeah. So this one is fine. Cannot find the symbol. We haven't made use of the this one symbol any clone anywhere. So I haven't initialized this one. So just give me a second here. 1 second. Mm, 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 mm. 1 second. So yeah, this is above itself, right? So this one, instead of the capital C, I have given the small c here. That is the reason we are getting the error. Yeah. So let me now let me hit the run button. This has to work. Let's see. Yeah, the sample test cases are getting passed here. So let me hit the submit button quickly, man. So this has to work. Let's see. This has to work for all the test cases. I hope it works. Yeah, you can clearly see here all the test cases are getting passed. So whatever the test, this one, whatever the code that we have written works absolutely correct for all the test cases, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.